Welcome. Today we tackle one of the most common constraints in industrial experimentation. You can only afford to run each treatment combination once. We will see why that single constraint changes everything about how you analyze data, and we will build the graphical tools that let you learn from an unreplicated design anyway. By the end of this session, you will be able to take 16 runs, no repeats, and confidently identify which factors are driving your response. Let us start with the core problem. In a standard factorial experiment, you run each treatment combination at least twice, and those repeat runs give you a direct, honest estimate of random error, pure error, in the textbook sense. That error estimate is the denominator in every F-test you want to run. Now take that away, one run per point, full stop. Suddenly you have no within-cell replication, which means no Tamir error, which means no denominator, which means no denominator, which means no F-test. Why would anyone design an experiment this way? Because in many real settings, replication is simply not possible. Each run might cost tens of thousands of dollars. Each run might take a week. Or, as in the example we will work through today, each run destroys the test specimen. You cannot go back and measure it again. So the unreplicated design is not a choice made out of laziness. It is the only option available. The question is, what do you do with the data you have? Two ideas. Rescue us. The first is a scientific assumption called the sparsity of effects principle. The second is a family of graphical tools that exploit that assumption. We will develop both. Here is the experiment we will carry through the entire lecture. A chemical engineer is developing a polymer coating process and wants to maximize film adhesion strength. Four factors are varied: temperature, which we will call A, catalyst concentration, B, coating speed, C, and solvent ratio, D. Each factor is set at two levels, high and low, giving a 2 to the 4 factorial with 16 treatment combinations. The critical constraint: every time you run a coating trial, the test substrate is destroyed in the adhesion measurement. You cannot retest it. So each of the 16 combinations gets exactly one run, one adhesion number, and that is all the data you will ever have from that substrate. The engineer's goal is to find which of these four factors and which combinations of factors actually move the adhesion needle so that future process development can focus on what matters. Let us look at the actual data. 16 rows, one per destroyed substrate. The factors are coded, +1 for the high level, -1 for the low. Notice that every possible combination of plus and minus ones across the four factors appears exactly once. That is the defining feature of a full factorial, and also the definition of unreplicated, no row repeats. The adhesion measurements range from about 36 up to 55. Run 16, where all four factors are at their high levels, gives the highest adhesion at 55.1. Run 9, where all four are at their low levels, gives the lowest at 35.7. But here's the critical point. We cannot tell from any single pair of runs whether a difference is real or just noise, because we have no second measurement to compare against. Every number in the adhesion column is unique, unrepeated, and irreplaceable. That is the challenge we are solving. Before we can understand why the unreplicated design is analytically difficult, we need to count degrees of freedom carefully. We have 16 runs, so 15 total degrees of freedom to work with. That is always the number of runs minus 1. Now let us count what we want to estimate. 4 main effects consume 4 degrees of freedom. 6 two-factor interactions consume 6 more. 4 three-factor interactions consume 4 more. And the single 4-factor interaction consumes 1 more. Add those up. 4 plus 6 plus 4 plus 1 equals 15. That is exactly the number of degrees of freedom we have. The model is saturated. Every single degree of freedom is spent estimating an effect. There is nothing left over, 0 degrees of freedom for error. And without error degrees of freedom, you cannot compute a mean squared error. You cannot compute a standard error for any effect, and you cannot run a single f-test or t-test. The saturated model fits the data perfectly by arithmetic necessity, not because the model is good. This is the fundamental problem of unreplicated factorial designs. Let us make this concrete by actually fitting the saturated model to the polymer data. The model includes every possible term, the overall mean, all 4 main effects, all 6 two-factor interactions, all 4 three-factor interactions, and the 4-factor interaction. Written out, that is 16 parameters for 16 observations. When you fit this model, something mathematically inevitable happens. The residuals are identically 0. The model passes through every single data point exactly. This is not a triumph of model fit. It is a warning sign. A model that fits perfectly has consumed all the information in the data just to describe itself. There is nothing left to measure noise, and therefore nothing left to test hypotheses. We need a different strategy. When you fit that saturated model and look at the analysis of variance table, you see 15 rows, 1 for each estimable term, and then nothing, no residual row, no error. The sum of squared residuals is 0 to machine precision. This is the dead end that unreplicated designs lead you to if you try to use classical ANOVA directly. Every degree of freedom has been spent. The model is exactly identified. You have 15 effect estimates and no way to judge which of them are real and which are just noise riding along for the trip. To move forward, we need to bring in an assumption about the world. Here is the assumption that makes unreplicated analysis possible. In real physical, chemical, and engineering systems, the world tends to be sparse. Main effects are usually the biggest drivers of a response. Two-factor interactions matter sometimes. Three-factor interactions are rarely important. Four-factor and higher interactions are almost never meaningful in practice. This is the scarcity of effects principle, and it is a scientific claim about how nature tends to work, not a mathematical theorem. You cannot prove it from first principles, but decades of industrial experimentation have validated it empirically across chemistry, manufacturing, biology, and engineering. The practical consequence is powerful. If we believe that three-factor and four-factor interactions are negligible, then their effect estimates are not measuring real phenomena. They are measuring noise. And if they are measuring noise, we can use them as a yardstick to judge whether the main effects and two-factor interactions are large enough to be real. Sparsity turns the high-order interaction estimates into a surrogate error term. That is the key insight. Now we have 15 effect estimates from the saturated model. Each one is computed as twice the corresponding model coefficient. That factor of 2 converts from the half effect scale of regression coefficients to the full effect scale that engineers prefer, representing the change in response when you move a factor from its low level to its high level. We extract all 15 estimates and sort them by absolute magnitude. This ranking is the raw material for our graphical screening tools. The question we are about to answer graphically is, which of these 15 numbers are large enough to be real and which are just noise? Look at the ranked effect estimates for the polymer coating experiment. At the top, temperature has an effect of positive 7.87, the largest by a wide margin. Catalyst concentration comes next at positive 5.22. The temperature by catalyst interaction is 4.17, and the temperature by solvent interaction is 3.20. Coating speed has a main effect of 2.70. Now look at what happens below that. The A by C interaction drops to 0.612. Solvent ratio alone is only 0.438. And from there, Everything else, all the 3-factor interactions, the 4-factor interaction, and several 2-factor interactions, and several 2-factor interactions is below 0.4, with most clustering near 0.1 or smaller. That gap between the top 5 and the rest is exactly what sparsity predicts. The bottom cluster is our noise reference. The top cluster contains our candidates for active effects. But we need a more principled way to draw that line than just eyeballing a ranked list, and that is where the graphical methods come in. Here is the key question. If all 15 effects were pure noise, if none of them were real, what would their distribution look like? Because each effect estimate is a linear combination of the observations, and the observations are independent with constant variance, the effect estimates would be independent and normally distributed, all centered at 0 with the same variance. Now, if you take 15 numbers drawn from the same normal distribution and plot them on a normal probability plot, that is, plot each value against the normal quantile corresponding to its rank, they should fall on a straight line through the origin. That line is your reference for inert effects. Any effect that is genuinely active will be larger in magnitude than the noise, so it will pull away from that line. Points in the upper right that lift above the line have large positive effects. Points in the lower left that fall below the line have large negative effects. The normal probability plot of effects is a visual hypothesis test. The line represents the null hypothesis that all effects are noise, and departures from the line identify the alternatives. To build the normal plot, we rank all 15 effect estimates from smallest to largest. For each rank I, we compute a normal score using the plotting position formula, the inverse normal of the quantity I minus 0.5 divided by n, where n is 15. This gives us the expected normal quantile for the ith order statistic. We then plot each effect estimate on the vertical axis against its normal score on the horizontal axis. The reference line is drawn through the central cluster, the majority of points that represent inert effects. Any point that drifts away from that line is a candidate for an active effect. The direction of drift tells you the sign of the effect. On the normal probability plot for the polymer coating data, the central cluster of points, the inert effects, forms a tight line near 0. These are the high-order interactions and a few small 2-factor interactions, all consistent with pure noise. Now look at the departures. Temperature A pulls strongly to the upper right. It has a large positive effect on adhesion. Catalyst concentration B also departs upward. The A by B interaction departs as well, confirming that temperature and catalyst do not act independently. Coating speed C shows a moderate positive departure. The A by D interaction also lifts away from the line. The direction of departure is informative. All the active effects here are positive, meaning that moving these factors from low to high increases adhesion. For the engineer, this is already actionable. Run temperature and catalyst at their high levels. But we want to confirm this reading with a second graphical tool before committing to a reduced model. The normal plot is powerful, but it has one mild inconvenience. Effects scatter on both sides of 0, so you have to track both tails simultaneously. The half normal plot solves this by folding the distribution at 0. Instead of plotting the signed effect, you plot the absolute value of each effect. And instead of normal scores, you use half normal scores, the inverse normal of the quantity I plus n, divided by 2n plus 1. This maps all effects onto the positive half of the normal distribution. The result is a one-sided plot where inert effects cluster near the origin in the lower left and active effects lift away into the upper right. There is no ambiguity about sign. You are purely reading magnitude. The reference line passes through the origin and through the inert cluster. Any point that rises clearly above that line is flagged as active. Practitioners often prefer the half-normal plot precisely because the pattern is unambiguous. You are looking for one thing in one direction. Building the half-normal plot follows the same logic as the normal plot, but we work with absolute effect magnitudes. Rank the absolute values from smallest to largest. For each rank I, compute the half-normal score using the formula, the inverse normal of the quantity I plus n, divided by 2n plus 1. Plot absolute effect on the vertical axis against the half-normal score on the horizontal axis. Draw the reference line through the origin and the tight cluster of small effects. Label each point so you can identify which term it represents. The visual task is then simple. Find the points that lift above the reference line. On the half-normal plot for the polymer coating experiment, the picture is clean and unambiguous. The reference line passes through the origin and to a tight cluster of small effects in the lower left. Those are the inert high-order interactions, all with absolute magnitudes below about 0.6. Above the line, 5 points stand out clearly. Temperature A is the highest, sitting well above everything else. Catalyst, B, and the A by B interaction are next, both clearly separated from the inert cluster. Coating speed, C, and the A by D interaction also lift above the line, though by a smaller margin. Compare this to the normal plot. The same 5 effects are flagged, but here the separation is visually cleaner because everything is positive and you are reading a single upper tail. This is why the half-normal plot is often the preferred tool in practice. The signal is easier to read, and there is less chance of missing an active effect that happens to be negative. Now that the graphical screening has identified the active effects, what do we actually do with that information? The answer is to build a Regit model, a model that includes only the active effects and any lower-order relatives required by the hierarchy principle. The hierarchy principle says, if you include an interaction, you must also include all the main effects that compose it. So if A by B is active, both A and B must be in the model, regardless of whether their individual main effects appear active. The terms you drop from the saturated model, the inert high-order interactions, do not disappear. Their degrees of freedom get pooled together to form the residual, which becomes your error estimate. This is the payoff of sparsity. By assuming those high-order terms are negligible, you convert them from wasted degrees of freedom into a usable error term. The reduced model now has a denominator for f-tests, and you can do formal inference. The graphical screening is what tells you which terms to drop and which to keep. Before we fit the reduced model, let us be honest about the limits of graphical screening. These plots are screening tools. They are not hypothesis tests in the classical sense. There is no p-value attached to the decision of whether a point is above or below the reference line. That is a judgment call, and borderline cases genuinely require engineering knowledge to resolve. Small designs with few effects can also struggle. If you have only 15 estimates and several of them are active, the inert cluster may be too small to anchor the reference line reliably. And the most important limitation of all, graphical screening identifies candidates, but it does not confirm them. The only true validation is a confirmation run, going back to the process, setting the factors at the predicted optimum, and checking whether the response lands where the model says it should. Treat the graphical analysis as the beginning of the investigation, not the end. Based on the graphical screening, we retain 5 effects in the reduced model, the main effects of temperature A, catalyst B, and coating speed C, plus the A by B and A by D interactions. The A by D interaction brings solvent ratio D into the model through the hierarchy principle, even though D's main effect was small. The remaining 10 terms, the inert high-order interactions and small two-factor interactions, are dropped from the model and pooled into the residual. This reduced model now has a residual with degrees of freedom, which means we can compute a mean squared error, compute standard errors for the effect estimates, and run f-tests. Let us look at what that ANOVA table tells us. The reduced model ANOVA table is the result we have been building toward. Let us read it carefully. The residual row now exists 10 degrees of freedom pulled from the dropped high-order interactions, giving a mean squared error of 0.422. That is our error estimate made possible by the sparsity assumption. Now look at the active effects. Temperature A has a sum of squares of 248 and an F statistic of 586. That is an enormous signal relative to noise. Temperature is by far the dominant driver of adhesion. Catalyst B has a sum of squares of 109 and an F statistic of 258. Also enormous. The A by B interaction has a sum of squares of 69.5 and an F statistic of 164. The A by D interaction has a sum of squares of 41.0 and an F statistic of 97. Coding speed C is the smallest of the active effects with a sum of squares of 29.2 and an F statistic of 69. Every single active effect has a p-value of essentially 0. These are not borderline calls. They are overwhelming signals. For the polymer engineer, the message is clear: maximize temperature and catalyst concentration and pay attention to how solvent ratio interacts with temperature. Coding speed also matters but is a secondary concern. One important caveat: these p-values are valid only if the sparsity assumption holds, that is, only if the 10 pooled terms really are negligible. If any of them were actually active, our error estimate would be inflated and our F statistics deflated. The graphical screening gave us confidence in that assumption, but it is an assumption nonetheless. There is a temptation, after fitting the reduced model, to run a formal lack of fit test to check whether the model is adequate. In a replicated design, this test is legitimate and informative. You compare the model residuals against the pure error from replicated points, and a significant result tells you the model is missing something. But in an unreplicated design, you cannot do this. The reason is structural. A lack of fit test requires pure error, variability estimated from repeated measurements at the same design point. We have no repeated measurements. Every design point was run exactly once, so there is no pure error to compare against. The residual in our reduced model is not pure error. It is the pooled sum of squares from the terms we assumed were negligible. Testing lack of fit against that residual is circular. You would be asking whether the model fits well relative to an error term that was constructed by assuming the model fits well. That is not an independent check. It is a tautology. This point deserves emphasis because statistical software will often produce a lack of fit test automatically when you fit a reduced model, and the output can look authoritative. Do not be fooled. When the design is unreplicated and the error term comes from pooled high-order interactions, any lack of fit test the software reports is structurally invalid. The denominator is not genuine pure error, it is the sparsity residual. The legitimate alternatives are: add center points to the design before running it, which gives you a small amount of pure error and a genuine curvature check, or run confirmation experiments at the predicted optimum settings and compare the observed response to the model prediction. Those are real checks. A software-generated lack of fit test on an unreplicated design is not. When you are reviewing someone else's analysis and you see this, flag it. Let us consolidate what the polymer coating experiment taught us. The saturated model confirmed the fundamental problem: 0 residual degrees of freedom, no error term, no formal testing possible. The sparsity principle gave us the conceptual foundation to proceed. Graphical screening, both the normal plot and the half-normal plot, identified 5 active effects: temperature, catalyst, coating speed, and 2 interactions involving temperature. The reduced model gave us a usable error term and confirmed those effects with overwhelming F statistics. And the practical conclusion for the engineer is direct. Adhesion rises with temperature and catalyst concentration, and the way those 2 factors interact means you need to consider them jointly, not independently. 4 practical lessons to carry forward from this analysis. First, graphical tools screen. They do not confirm. The plots identify candidates. Confirmation runs validate them. Second, engineering context is essential for borderline effects. A point that sits just above the reference line might be real or might be noise. Process knowledge is what resolves that ambiguity, not the plot itself. Third, when you see a lack of fit test reported after model reduction in an unreplicated design, treat it with skepticism. It is almost certainly using the sparsity residual as its denominator, which makes it circular and invalid. Fourth, confirmation runs are the gold standard. Before you change a process based on a screening experiment, go back and verify that the predicted improvement actually materializes at the settings the model recommends. Now it is your turn to work through a parallel example. The setting is injection molding. A manufacturer wants to reduce part shrinkage. Lower is better. All factors are varied in a single replicate: 2 to the 4 factorial, mold temperature, injection pressure, cooling time, and gate size. 16 runs, 1 shrinkage measurement per run, no replication. The analytical task is identical to what we just did with the polymer data. Fit the saturated model, extract all 15 effect estimates, build both graphical screening plots, identify the active effects, and fit the reduced model. Work through this before looking at the walk solution on the following slides. Here is the injection molding design matrix. 16 runs, 4 factors coded as plus and -1. 1 shrinkage measurement per run. The shrinkage values range from about 13.6 up to 26.8. Notice that run 16, all factors at their high levels, gives the highest shrinkage at 26.8, and run 1, all factors at their low levels, gives the lowest at 13.6. As with the polymer data, your first step is to fit the saturated model and extract all 15 effect estimates. The structure is identical: 16 parameters, 16 observations, 0 residual degrees of freedom in the saturated fit. The graphical screening is what will rescue us. The procedure for extracting effects is the same as before. Fit the saturated model with all main effects and interactions. Each effect estimate equals twice the corresponding model coefficient. That factor of 2 converts from the regression half effect scale to the full effect scale, representing the change in shrinkage when you move a factor from low to high. Extract all 15 estimates and sort them by absolute magnitude. This ranked list is the input to both graphical plots. Look at the ranked effects for the injection molding data. Mold temperature has the largest effect at 5.87. Moving from low to high mold temperature increases shrinkage by nearly 6 units. Cooling time is next at 4.17. The mold temperature by cooling time interaction is 3.06 substantial, meaning these 2 factors do not act independently. Injection pressure has a main effect of 2.10. Now look at the drop-off. Mold temperature by injection pressure falls to 0.817. Gate size is only 0.508. Everything below that, injection pressure by cooling time, all 3-factor interactions, the 4-factor interaction, and several 2-factor interactions, is below 0.43, with most clustering near 0.1 or smaller. The sparsity pattern is clear. A small number of effects are large, and the rest are small and scattered near zero. The high-order interactions are doing exactly what sparsity predicts. They are negligible, and they will become our error pool. The graphical plots will formalize this separation. To build both plots, apply the same formulas we used for the polymer data. For the normal plot, rank the signed effects and compute normal scores using the plotting position I-0.5 divided by n. For the half-normal plot, rank the absolute effects and compute half-normal scores using I plus n divided by 2n plus 1. Plot. Draw the reference line through the inert cluster and label the departing points. The question you're answering is, which effects are large enough to be inconsistent with the null hypothesis that all effects are noise? The half-normal plot for the injection molding data tells a clear story. The reference line passes through the origin and through the tight cluster of small effects in the lower left. Those are the inert high-order interactions and small two-factor interactions. 3 points lift clearly above the line: mold temperature, cooling time, and their interaction. These are unambiguously active. Injection pressure is a borderline case. It sits above the inert cluster but is not as dramatically separated as the top 3. A practitioner would note injection pressure as a candidate and consider whether process knowledge supports including it. Gate size and all high-order interactions hub the reference line and will be pooled into error. The normal plot tells the same story. Mold temperature and cooling time pool to the right. Their interaction also departs, and injection pressure is a moderate departure. The consistency between both plots increases confidence in the screening decision. Based on the graphical screening, the reduced model for injection molding retains mold temperature, injection pressure, cooling time, and the mold temperature by cooling time interaction. Injection pressure is included because it was borderline active and the hierarchy principle requires it anyway once we include the mold temperature by injection pressure interaction, though in this case we are including injection pressure on its own merits as a borderline active main effect. The remaining terms are dropped and pooled into the residual, giving us the error degrees of freedom we need for formal testing. The reduced model ANOVA for injection molding confirms the graphical screening. The residual row carries 11 degrees of freedom, giving a mean squared error of 0.486, our error estimate from the pooled inert terms. Mold temperature has a sum of squares of 138 and an F statistic of 284, an overwhelming signal. Cooling time has a sum of squares of 69.6 and an F statistic of 143, also overwhelming. The mold temperature by cooling time interaction has a sum of squares of 37.3 and an F statistic of 76.8, clearly active. And this is important. It means the effect of cooling time on shrinkage depends on what mold temperature you are running at. You cannot optimize cooling time without specifying mold temperature. Injection pressure has a sum of squares of 17.7 and an F statistic of 36.4 with a p-value of 0.0001. That is small enough to be convincing. Injection pressure is genuinely active, and the borderline call from the graphical screening was the right instinct. For the injection molding engineer, the practical message is, mold temperature and cooling time are the primary levers for reducing shrinkage, and they interact, so you need to set them jointly. Injection pressure is a secondary lever worth controlling. Gate size appears to have negligible effect and can be set for convenience. The next step in practice would be confirmation runs at the predicted low shrinkage settings and possibly a response surface experiment to find the true optimum in the region identified by this screening. Let us close with the key takeaways from the injection molding practice example. Sparsity was confirmed. The higher-order interaction estimates were all small and consistent with noise, validating the assumption that let us pull them into error. Graphical screening, both the normal and half-normal plots, identified the same three active effects consistently, which is exactly the kind of agreement you want to see before committing to a reduced model. The reduced model yielded a valid error term with 11 degrees of freedom, enabling formal f-tests that confirm the graphical findings. And the practical next step is clear. Run confirmation experiments at the predicted optimum settings, and if the response surface in the region of interest is curved, plan a follow-up response surface design to map it. Graphical screening of unreplicated factorials is the beginning of the optimization journey, not the end.